In Learning Target 6, we're talking about vertical asymptotes. We've talked about asymptotes in pre-calculus before. Those are those imaginary lines that your function can't cross. Right? They get really, really close to it and hug that line, but they never actually cross it. Okay? So for a vertical asymptote here, the definition kind of goes along with what we talked about with limits. So if a function approaches infinity, or negative infinity, as x approaches some value from the right or left, then the line x equals c, that's a vertical line, is a vertical asymptote of the graph. All right? If the graph of a function has a vertical asymptote, then that function is not continuous at c, so we have a discontinuity like we talked about. So here are some examples. Here's the function 1 divided by the quantity x minus 1. Well, if I put 1 into the denominator, I have 1 divided by 0. And we know we can't divide by 0. There's no way to simplify this function, and so I have a non-removable discontinuity, right, at x equals 1, and so there happens to be a vertical asymptote there. Okay? Over here, another function, 1 divided by the quantity x minus 1 squared. Same thing, if I put 1 into the denominator, I have 1 over 0, can't divide by 0, so I have and I can't simplify this, so I have a non-removable discontinuity at x equals 1, also a vertical asymptote. Another example, this one has negative 1 divided by the quantity x minus 1. Same idea, you put 1 into the denominator, you get 0, you can't have that. So non-removable discontinuity at x equals 1. Same thing here, you have negative 1, so non-removable discontinuity at x equals 1, all right? So if you're looking at all of these, by definition, if you have a vertical asymptote, that means that after dividing out common factors, so if you can remove removable discontinuities, then the vertical asymptotes occur at x's that make the denominator equal to 0. That's what just happened on all 4 of those graphs. Okay? So we're going to find some vertical asymptotes here. So for A, we're determining all vertical asymptotes of the graph of each function. So for A, we have 1 divided by 2 times the quantity x plus 1. So again, we're looking for what x values cause the denominator to be 0. So in this case, what x value causes the denominator to be 0? X equals negative 1, right? We have 1 divided by 2 times negative 1 plus 1. Well, then I would have 2 times 0 and be 1 over 0, and that would be a problem. All right? So at x equals 1, there's a non-removable discontinuity, and therefore there's a vertical asymptote at the equation x equals negative 1. Let's look at a graph of that. If we're right, there we go. There's the function, and you can see there's a vertical asymptote at x equals negative 1. So again, we're just looking to see where our function is undefined, okay? Let's look at B. Again, what x values cause the denominator to be equal to 0? Well, for B, I cannot factor the numerator, all right, because it's x squared plus 1. In the denominator, though, I have x squared minus 1. So this is x squared plus 1 divided by x minus 1, x plus 1. So what values, because there's 2, cause the denominator to be equal to 0? Well, x equals 1 and x equals negative 1. If I substitute either of those numbers into the denominator, so if I put 1 here, I have 0 times some quantity, right? 1 times 2. If I Put negative 1 here. I have negative 2 times 0, so I get 0. So both of those cause the denominator to be 0. I cannot factor anything. I cannot cancel out any common factors because I cannot factor x squared plus 1 in the numerator. Right? There's a plus sign in the middle. Because of that, to find two numbers you can multiply to get 1 that add up to be 0, and that doesn't really work that well when you have plus sign. So we have two values here. Both are non-removable discontinuities. And so both are vertical asymptotes. Let's look at the graph and confirm. There's the graph. Since there's two vertical asymptotes there, so you're not just restricted to just one. All right, on C, we have cotangent x. Now, cotangent x is trigonometry. We did that at the beginning of the year. So cotangent can be rewritten as cosine over sine. So now I need to know what values cause sine of x to be 0. So in other words, where is sine x 0? So we're going to need to look at the unit circle, your favorite. So here it is. Remember, we don't have this in a while, so we always have a coordinate that's cosine, then sine, right? So sine is 0 at 0. Sine is 0 at pi. Sine is 0 at 2 pi. And if you kept going around, this would be 3 pi, and then at 4 pi, and then at 5 pi, etc., 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 etc. Right? So that means that it's going to be undefined a lot. So where is sine x equal to 0? At all integer values of n. If you have n times pi, right? Integer values, so at 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. Not any of those fractional values, because the rest of those are not 0. Okay? So that means there are going to be an infinite number of vertical asymptotes or non-removable discontinuities all right? And so if you look at the graph, you can see there they are. At every single integer value of pi, there's a vertical asymptote, including the y-axis. It's just not dotted in blue because the y-axis is actually part of the graph, but it would be an asymptote as well. You can see they just keep going, keeps repeating. Okay? All right. One more example. Determine all the vertical asymptotes of the graph. And we have a function here, and it looks like we can definitely factor the denominator, and we might be able to factor the numerator even. Again, if you can remove a discontinuity, then it's not a vertical asymptote. Okay? So the denominator is the easy part. X squared minus 4 is the same as x minus 2 times x plus 2. So right now, it looks like there's two discontinuities. One at x equals 2, one equals x equals negative 2. All right? Both of those are discontinuities. Both of those are possible vertical asymptotes. Okay? But we got to see if we can cancel out any common factors. So in the numerator, I'm looking for two numbers I can multiply to get negative 8 that add up to be positive 2. X plus 4, x minus 2, right? 4 times negative 2 is negative 8, and 4 plus negative 2 is positive 2. So it looks like I can cancel out the x minus 2's, right? Well, so those factors involved this discontinuity. When you put 2 in, you got 0. So in this case, this is a removable discontinuity, right? So that's not a vertical asymptote. So we really have the equivalent function x plus 4 over x plus 2. And so now I cannot simplify anymore. And if I put negative 2 in for x, I'm still going to get a denominator that is 0, because negative 2 plus 2 is 0. And so here, I have a non-removable discontinuity. And so there's going to be a vertical asymptote at x equals negative 2. So let's check that. Here's a graph. So you can see there's a hole at the removable discontinuity. There's an asymptote, though, at the non-removable one. Okay? That's all learning target 6 is. You're going through, and you're going to the same methods we've been talking about of factoring, rewriting things, to see if there are removable discontinuities or non-removable discontinuities. And once you've simplified everything, if there's a non-removable discontinuity, there's probably a vertical asymptote there. Again, you're looking for values of x where the denominator would be 0.